Welcome to Freeslate's webinar on automatic solutions to accelerate drug development. This is the 9th webinar in our ongoing series on this topic. My name is Dave Yamane. I am the Product Marketing Director for Life Sciences at Freeslate, and I'll be your host today. Today, you will hear a presentation of some work we performed as part of our collaboration with Medicines for Malaria Venture. We're pleased to have Dr. Phu Sun from Freeslate join us today. Time permitting, we will conclude today's webinar with a brief questions-answer session at the end. Before we begin, let me invite you to submit questions using the chat menu on the lower left side of your screen. In the chat window, you can type in your question and press the Submit button. Any questions that we did not get to will be answered privately in a follow-up email message. Before we get started, I'd like to give you some background on malaria and Medicines for Malaria Ventures. Well, malaria is a life-threatening disease caused by 4 Plasmodium parasites. The disease is transmitted through bites by the Anopheles mosquitoes, and symptoms appear 8 to 25 days after being bitten by an infected mosquito, and it can appear flu-like. Symptoms include moderate to severe shaking, chills, high fever, profuse sweating as the body temperature falls, headache, vomiting, and diarrhea. Well, 150 to 200 years ago, malaria was endemic worldwide. But today, malaria is mainly prevalent in the tropical and subtropical areas of the world. In these areas, rainfall, warm temperature, and stagnant water provide an ideal environment for mosquito larvae. Areas of highest occurrence are Africa, south of Sahara, and parts of Oceania. Worldwide, there are 3.3 billion people at risk of contracting malaria, which is about 50% of the world population. There are approximately 247 million cases of malaria and approximately 1 million deaths from the disease every year. 90% of the fatalities occur in sub-Saharan Africa, and 85% of the deaths are children under the age of 5 years old. Well, from 1975 to 1999, there were 1,393 new drugs introduced by pharmaceutical companies, and only 4 of those were for treating malaria. New treatments are needed because malaria is becoming resistant to traditional methods to treat the disease. And so in 1999, a group from the World Health Organization founded Medicines for Malaria Venture to focus on developing new therapeutics against malaria. In the beginning, when MMV started, they had no compounds in their pipeline or any active projects. Since then, through their efforts, in 2013, they had 37 active programs, 6 compounds in Phase 2B or Phase 3 clinical trials, and has 6 drugs approved. Their current approach to discovering new novel chemotypes is mining the Plasmodium falciparum genome, studying the known biochemical pathways involved with malaria, and leveraging high-throughput screening to identify compounds active against the malaria virus. The high-throughput assay they use is a whole-cell imaging assay using DNA-specific dyes, and the assay has a hit rate of 0.5 to 1%, and several novel anti-malaria chemotypes with sub-micromolar activity have been identified. One of those screens was run at St. Jude's Children's Hospital. From the screen, a series of tetrahydroisoquinones were identified which have progressed to the lead optimization stage. The molecules that were the most interesting are have carboxylic acid 2 as a key intermediate, and carboxylic acid 2 is in the lower right-hand corner. Synthesis of the carboxylic acid 2 yields a racemic mixture, so an efficient method was needed to isolate carboxylic acid 2. So to prepare an enantiomer of carboxylic acid 2, a 4-step synthesis was employed by MMV. 2 of the 4 steps were for chiral resolution purposes, and an initial assessment by MMV to resolve the chiral mixture proved to be challenging. So as a result, MMV and Freeslate established collaboration to assess the viability using chiral salt resolution and high-throughput research to isolate carboxylic acid 2. To do this, we used our pre-formulation workflow. The pre-formulation workflow is configured for high-throughput solid form and crystallization screens. The system has weighing, heating, cooling, mixing, and liquid handling elements to completely automate the solid form screening process. Today, our speaker is Dr. Phu Sun. Dr. Sun is a research scientist at Freeslate, where he works in the Managed Research Services Group for small molecules. His group provides high-throughput screening services to pharmaceutical and biotechnology customers, including optimization, organic transformations, and solid form screening. Dr. Sun received his BA degree in chemistry from Hanover College and a Ph.D. degree in organic chemistry at Penn State University under the tutelage of Professor Stephen Weinrib. His graduate research focused on natural product synthesis. The title of Poo's presentation today is Advancing a Therapeutic for Treating Malaria by Identifying a Challenging Diastereomeric Salt for Chiral Resolution using High-Throughput Research.
Thank you, Dave. So this research is, as Dave just said, is a collaboration between Freeslate and MMV. In this case, MMV has Dave Soit and John Wan from Rutgers University that collaborated with us. So before I get into the detail of this talk, I just want to highlight what we have been able to achieve through a very short period of time. Like what David said, so racemic compound 2 would need to be, that was through a synthetic step, but there are 2 additional steps just for the purification purpose, which I will illustrate later. If they have actually tried to do chiral resolution alone, but the result was fairly poor. It could not be really scaled up for other purpose. Through this collaboration, relatively short period of time, we were able to achieve 85% yield with a fairly pure E separation. Let me get into the the comparison between traditional research and high-throughput research first. Typically, in a lab setting, without high-throughput approach, what we can typically do is a few experiments at a time. So that's a fairly inefficient exploration of experimental space, and all the work has to be done by hand. So it's fairly labor-intensive, and there's definitely a chance for human error. And because we can't really explore, a route efficiently, we might abandon the, promising route too early, because we really don't see that hit the way we choose our variables. If we do a high-throughput approach, we actually can systematically explore a set of variables in a very scientific manner, and because automation help us do a lot of the labor-intensive work, they listen to what we set up to do, so they eliminate a lot of error-prone, manual-intensive steps. And you will see the scale is relatively small compared to if you do it in a lab setting. So we can use a fairly small amount of material to explore a lot of experimental space. But before we can do all of this, what I want to emphasize is science is still behind everything we do here. We still have to have a valid approach. It's not like we can just screen everything, because there are still too many experimental variables that can be screened. So we still have to understand the problem at hand to decide what kind of variable to screen, what's more important than the others, because if we do it the right way and understand the interaction between different variables, we can sometimes have very serendipitous discovery, and we can see the whole big picture. If you set up that screen correctly, you can see the whole big picture very clearly, and we can first quick abandon the route that doesn't look right, and we can rapidly pinpoint a more advantageous route. And there are definitely trends and clues you see when you screen all different conditions closely. Like what I said before, also small scale, you definitely allow you to explore a variety of different conditions with small amount of material. So how do we define these variables? At the end, we understand the problem. We try to understand the problem. We try to narrow down what kind of variables we want to screen, right? So what we try to do here is try to categorize what kind of defining factors we should think about. First of all, is our research goal. There's two different type of, one is exploratory. So the chemistry is not really known. If people want to see if that, for example, that transformation is possible, it's never been done before. It's more discovery. So a lot of broad screening, a lot of maybe not a lot of hits. And another more common type for high throughput research, like what we do in our lab, is optimization, process optimization. So the process has been known. Typically, when a customer comes to us, they have a process in hand already, but obviously there's some deficiency in terms of what they want to achieve. They might want a higher yield. In this case, they want to have a better way to separate this racemic compound. A lot of time it's an impurity they have a hard time getting rid of. They want to see if there's a better way to get rid of this impurity. That could be only like 1 to 2%. They want to see if they can even go lower. A lot of times they desire alternative conditions because maybe the process they use now is patented. They want to see if there's non-patent approach to this. And after we kind of understand what needs to be done, and we have to see what has been done in the lab, and what kind of similar work has been done in the journals and the patents. After all this, one thing that is fairly important is it has to be available, right? A lot of times you see what's in the literature is it seems like a very nice ligand, a very nice catalyst, but you really cannot buy it. You cannot really get hold of it. So there's nothing you can do. So you need to understand what you can buy, what you can obtain. The final thing is the scientists, their instinct, their intuition. Typically, their resources are limited. They can only try, they can only try certain things before they either move on to the next approach or decide to call it quit. But a lot of times, there's a lot of other ideas they want to try, but they don't really have the resources or time to do it. Like what I said, high throughput approach give you that opportunity to try a lot of different conditions. So let's talk about what kind of variables that is out there, right? So there are two main type of variables. One is called discrete variables. Another one is called continuous variables, right? So discrete variables are something that is limited amount in number, right? Catalyst, precursors, ligands, solvents, counterion in this case, acid base. There are just that many you can obtain. Typically, we do a full factorial design, so we kind of cover every combination of the variables we pick. So this is very ideal for an initial screening to narrow down the key discrete variables that is important for this experiment. A lot of time, because if you do full factorial, there's a lot of interesting combinations that is not obvious before the screening, but it become a hit. So what does that encourage is non-intuitive discoveries. And also with the full factorial design, a lot of time it can help you observe the underlying trend more clearly because you have every combination covered, so you can sort of see what's trend in terms of changing variables. So after the key advantage discrete variable has been decided, has been kind of narrowed down, then continuous variables such as equivalence, concentration, solvent ratios, a lot of things that is is not a fixed number, but it can be 1.2 equivalent, 1.25 equivalent. So you can start deciding what's more important in terms of that type of variables. And it's very ideal for a follow-up screening when the discrete variables has been identified. So here, I just want to give you a quick example what a full factorial design looks like, right? So in this case, just for illustration, we have 12 chiral resolution agents and 8 solvents. So we typically put up 96 well plate design. In this case, it's 12 chiral resolution reagents and 8 solvents. Typically, in a design, we always, put a known condition as a reference or control. In this case, when the screening is done, that particular condition should give us similar results that is done in the lab. A lot of time, even before the full plate is done, for example, in this case, A1 condition is a known condition. We'll actually do a test run that is small scale, that's the scale of the plate design, and to see if we can replicate the yield and the EE of the regular design, the regular lab scale. So when we're confident, we can actually do the whole full plate under high throughput conditions. So after we have done the full the first plate, there's several potential outcomes. So one of the good one is we actually have fairly promising hit. So typically what we will do is we'll try to scale up the condition that it looks like a hit in our plate, just to see we can replicate it back to the regular scale, lab scale, to see if that was still a hit. A lot of time the whole plate doesn't look promising. And we are pretty confident, and especially with the reference cell, similar to what the lab scale condition looks like, we're pretty confident the route is not going to work. So we abandon that particular route. But a lot of times what happens is it just gives you some clues and trends, so it helps you build up another follow-up plate. So the most typical one is you do have some hit. You will see in this particular case later on, that's exactly what happened. So we definitely get clues about what's happening. So we design our follow-up plate based on the result from the initial screening. But other possibility is because you have so many other discrete variables you were not able to include in our first plate. You try to include more into it, and there's other experimental conditions that you can get hint out of. Maybe the temperature a little bit too high, there's too much impurity, you want to lower the temperature a little bit, things like that. You're kind of fine-tuning your follow-up plates based on what you have seen from the initial screenings. So you can do this iteratively until you move your project forward. So now let's get into the talk. So like what I said earlier, so initially, Rector's route is there's two different ways for them to approach this. For a relatively big scale, so what they actually have to do is you see from so initially they have to, the carboxylic acid, they have a hard time resolve this. So what they did is they made ester out of it, and then they used a chiral supercritical fluid chromatography in a preparative scale to separate racemic 3, the +3 and -3. Afterwards, they have to hydrolyze it using lithium hydroxide in methanol and water, so to give you back the desired +2 and undesired -2. So the yield and the separation is perfect, but now the two synthetic steps involved and the chiral column involved makes it still not ideal for a much bigger scale. So they did try the chiral resolution route, and what they have discovered is amino alcohols appear to be fairly promising, which is, you will see, how we started our screening as well. But the the result they're getting from their quick screening wasn't really promising. So they get the E is good. The E is relatively fairly good, but the recovery is poor for them to scale it up. But they do. You will see this 1 amino 2 indinol, which is what they used. So what do we have to do here at Freeslate? So in essence, when you do this chiral resolution study, it is actually a solubility study. What are you trying to study? You're trying to use a particular chiral resolution reagent to make a salt. You make this +2 salt and -2 salt. So in essence, you're trying to study the solubility difference between these two salts. So what you want to achieve is the minimum solubility of this +2, because you want the +2 to be precipitated out so you can collect them. You want this -2 salt to be very soluble so you can wash it away. So the goal is very simple. When you distill to it, it's maximum solubility for unwanted diastereomer while minimizing the solubility of desired one. In this case, +2 salt. So in terms of variables, you can solve it, right? So you obviously have counterion you have to think about. But in terms of solvent, what kind of solvent out there, right? You have single solvent, like alcohols, esters, ethers, ketones, aromatics. But there's just that many. So you can sort of tinker with. But what's more important is also important is a solvent combination, right? So when you have solvent combination, you have become unlimited amount of variables you can play around with. So when you add a solvent, we call it modifier. A lot of times it's water or heptane. So you can use that type of solvent to fine-tune the solubility difference. And also, one thing I want to point out is when you fine-tune it, you want to make sure water or heptane is miscible for that particular solvent. So let's look at this. Before we do the screening itself, we have to think about what we're going to screen. And as you can see here, is we picked 8 chiral amino alcohol, including the one that they have screened. But they're all, so in a way, this is a kind of a focus screen already. We didn't really pick all the chiral amines out there. We only pick a diverse group of chiral amino alcohols. So in a way, this is a kind of a focus screen already. And also, we picked 12 solvent or solvent mixture, including the solvent mixture they have screened as well. And the condition, experimental condition we have is, as you have seen here, is we use about 32 mix of racemic 2, 1 equivalent of chiral amino alcohol, and we have a couple of different solvents, which I will show you the step we do to make the whole experimental work. And the concentration as listed. And the layout, the library layout is on the lower left. It's here. So we have 12 solvent mixtures and 8 chiral amino alcohols. Another thing we need to do is prepare chiral HPLC. Typically, when the experiment is done, when the experiment is given to us, there are some chiral analytical method available already. We can either adopt that particular method, but a lot of times the method is fairly long, and we try to shorten it as much as we can because we have to do a lot of analyticals because there's a lot of conditions we would like to analyze. In this case, the chiral separation typically is difficult, so the method is still fairly long. It's about, as you can see, about 12 minutes per analysis. If it's a chiral, 1 or 2 compounds, sometimes we can shrink it to 2, 3, 4 minutes. But here, because it's chiral separation, is still longer than normal. Now, let's take a look at how we actually have done it in the lab. So we use our powder dispense capabilities to dispense the desired amount of racemic 2 into each vial. And then we use our CM to dispense counterions. So in this case, we have 8 counterion solutions we made in methanol. So in this case, the salt formation step, we use a common solvent. So we have not really used the solvent variables I've shown you earlier. We use methanol alone. The reason for that is we want to make sure that the salt formation is complete. The methanol is, or sometimes ethanol is very good for this purpose. And we will stir it at 45 degrees for 2 hours to make sure the salt is formed. After that, we'll remove the methanol before we introduce the 12 solvent mixtures. So at the second day, we'll dispense this 12 solvent mixtures. Is 500 microliter per well, and seal the plate. And then what we'll do is we'll do this temperature profile. So we'll start with 50 degrees stirring and gradually dropping the temperature over time. And the last hour, few hours, we'll stop the stirring. So make sure the compound will, whatever is not soluble will gradually precipitate it out. And then the third day, because the whole temperature profile will take a day. The third day, what we'll do is to use our filter assembly. So the whole plate is still sealed. So what we'll do is we'll take the supernatant out, and filter it, and then dilute it to 10x and 100x, so we can do chiral analysis. But typically, when we do solubility studies, we'll obviously do analysis for the whole plate. But for chiral resolution studies, we actually do not need to do the whole plate. So after the HPLC plates are prepared, before we do the analysis, what we'll do is we'll open the master plate. The master plate is where you have all the preparation has been done in this master plate. What we'll do is we'll open it up and see wells that have solid. A lot of wells will be dissolved. So if both, so in this case, we're trying to study the solubility difference. If both counterions, both salt have been dissolved, so there's no point because they're both fully soluble. So what we'll only analyze are the wells with solid in it. So that's only wells with the possibility of resolution. As you can see here, all the chiral amino alcohols we picked, the one that initially was the one amino indinol was actually the hit, the very moderate hit in ethyl acetate, better than their initial screening, but it's still very modest. So what we actually do observe is many fully dissolved wells, which is not good. That means the solubility is just too high. And another hint, maybe the counterion, the equivalent-wise is the whole plate we screen is 1-to-1 equivalent. Maybe we need more counterion for the salt to be formed. So since the hit is still amino indinol, other things fail to show up. So the second follow-up, we actually fix it on this amino. So in this particular case, the hit is a trans. We're thinking maybe cis is a possibility that will work. And we want to test both the 2 equivalents and 1 equivalent of the counterion. And then one of the big observations marked in red is a lot of wells are fully soluble. Like what I said earlier, the key to this study is to study the solubility difference, and the solvent is crucial. So what we're trying to do here is, if the solvent, all the salt form is too easily, readily dissolved, we need to lower the solubility. In this case, what we have done is, you will see in the next slide, is we add heptane to a lot of our screening solvent to intentionally lower the solubility. Whatever the solvent it is, we add one-to-one, amount of heptane to make sure the solubility is low enough. Certain, one of the salt will be, hopefully not soluble. As you can see here, the design here is not really fully factorial, but we do start doing 1-to-1 and 1-to-2 equivalents, and we focus on this chiral amino alcohols, and we start using different. As you can see here, we start using different acetates, alcohols, propylnitriles, ethers, ketones, toluenes. But for a lot of them, what we did is we add heptane to it to make sure the solubility is not too high to dissolve both. So the hit we gain is propylnitrile in heptane, 1-to-1 ratio, and the amount of alcohol needed is 2-to-1. So like what I said here is 2-to-1 ratio of this amino indinol is needed, and the 1s, 2s, this particular chiral amino indinol will lead to this +2 salt to be non-soluble, which is what we want. The desired one to be non-soluble. As you can see here, in this particular situation, which is 1-to-1 propylnitrile heptane, the -2 salt has about 27.5 mg per ml solubility. It's about 30 mg, just say roughly 30 mg per ml. And you will see the +2 salt only have about 0.03 mg per ml. In essence, there's about 1,000-fold difference between these two salts, which is fairly dramatic. It was, when we actually initially saw the data, we were surprised and elated. It was totally beyond our imagination. As you can see here from the HPLC analysis we have done, the +2 salt is barely soluble and is desired. So a lot of them is stayed in the solution. It stay as a solid, and the -2 has a much higher solubility. So now, so what do we do from now? Typically, because the result was so dramatic, so the next step, instead of doing another follow-up, we decided we need to do a scale-up. The scale-up is actually done in Rutgers University. You will see the result a little bit later. But before we actually we're going to do the scale-up, we would take a closer look at the result we're having here before. So instead of duplicate exactly what I have done in the lab, we want to see if there's additional modification we need to do before we do the scale-up. So in this case, like what I said earlier, is we want to make sure the -2 salt, the undesired one, is as soluble as possible, so to maximize the EE of the solid. So what we want to do is want to ensure this -2 salt is fully dissolved in solution. So let's study our screening condition a little bit more to see what we actually get. So maximum concentration for each isomer salt is about 32.5 mg per ml. And in solution, we get about 27.5 and mg per ml -2 salt solubility. So in a way, not all -2 salt has been dissolved. You see the discrepancy here between what can be dissolved and what was dissolved. So the difference between these two numbers, that means there's still some -2 that is stuck in solid, which is not good, because that will, the reason it lower the EE of the solid. So in a way, our initial screening, which we don't know what's happening, but now after we analyze the data, we know 500 microliter of this particular solvent is not sufficient to dissolve the 32.5 meg of this racemic 2 to ensure full -2 solubility. So what do we have to do here is pretty obvious. So what we need to do is using more of this solvent, 1:1 propionitrile heptane solution, to make sure the salt is completely dissolved. Obviously, every time you use more solvent, there's a trade-off, right? The more solvent you use, the more desired solid becomes soluble. But in this case, because the solubility of +2 is so minor, additional solvent will contribute very little to the to the solubility of +2. So the trade-off is minimal. So more solvent is definitely helpful for you to eliminate the -2 salt, but barely dissolving more +2 salt, which is really good. So this is a scale up done at Rutgers University. As you can see here is what they did is 16.4 grams of racemic 2 with two equivalents of this 1S, 2S amino alcohol. So the first step, typically when you do scale up, when we do the experimental stage, we want to make sure all the solid form, so we use methanol for the whole salt formation step. But in this particular case, we're going to do reflux. The methanol salt formation step was eliminated, and so we use 500 mils of this solvent mixture. If you calculate it, 300 mil is minimum amount of solvent needed to dissolve all the +2 salt. So you have an additional 200 microliter to make sure all the -2 salt has been dissolved, because you want the solid collected to have the highest EE possible. And one amazing thing initially was puzzling to everyone is typically when you do this kind of experiment, when you do the reflux, make sure everything is dissolved, and then you cool it down, the one you want will gradually precipitate it out. But in this case, because the +2 salt was so insoluble, when the salt is formed, it immediately precipitated out, even under reflux. So the reflux was actually a slurry. Slurry is observed during reflux, which typically you don't see, but because the solubility is so low, refluxing condition will still not nearly enough to dissolve all the salt form for +2. And after you cool it, and additional 200 microliters of propionitrile and heptane was used to wash the solid to make sure the -2 salt is completely clean out of the solid. And after that, the salt, the +2 carboxylic acid is released using this citric acid aqueous wash and acetate extraction. As you can see here is after all this process, 7 grams of this +2 is obtained with really high 99.3 EE. As you can see here, the yield is about 85%. In essence, if you look at the number, is out of this 16.4 gram, you have about 8.2 grams of +2. Out of this 8.2 grams of +2, 7 grams was obtained with high purity. So in summary, what we have seen here is before, like we have 2 additional synthetic steps just for the purification purpose, and the initial resolution was have fairly poor yield. Through about 144 conditions later, about 2 weeks. This 2 screen took about 2 weeks to screen, 1 plate each, and we were able to obtain a condition that afford 85% yield with 99.3% EE. So in these 2 rounds of screening, we were able to identify a very optimized condition to achieve high EE and high mass recovery, because the analysis we did after the second round, the scale-up condition is actually even better than the screen condition. So that will conclude my talk.
Thank you, Pooh. We will now have a brief question and answer session. So Pooh, why did you eliminate the salt forming step in the methanol during scale-up?
Okay. So typically this is, when you set up a screening, there's a variety of different conditions. The methanol step was introduced to ensure the salt formation, because there's if you just introduce the 12 solvents for the salt forming step, then you're risking a lot of them the salt is not even being formed, because either the carboxylic acid 2 is not soluble, or your chiral counterion is not soluble. So to eliminate that, so for the screening purpose, you introduce a common salt forming step in a common solvent to make sure the salt are formed. But when you're doing the scale up, this salt forming step is just another step that you should attempt to get rid of. So that's exactly Rutgers chemists they did. So instead of in methanol, what we're trying to do, because there's reflux involved and the continuous reflux involved, so the salt forming step is eliminated, and it still get where you want to go without introducing another solvent. So the methanol step definitely serve a very good purpose during the screening, but during the scale up, we try to eliminate it to shorten the step during the real process.
Pooh, the next question is, how was all the HPLC data collected and analyzed?
So we typically, if you do a lab experiment, you can do a TLC, you can do HPLC. It's just one-off, you run it. But in this case, a lot of time you have a lot of data. So what we have to do here is we use our Freeslate software, what we'll do is we'll run the whole plate. In this case, we didn't really run the whole plate, but there's still a lot of conditions we have to run the HPLC analysis. And the data, if it just only stuck in the its own computer, and if you pull out every one of them, that's impossible to actually analyze the pros and cons of different conditions. So what we actually do here at Freeslate is we use a software called Automation Studio. What the Automation Studio will do is to help, the chem station is the software that runs the HPLC analysis. But the Automation Studio will do is tell, after the chem station runs analysis for all the different conditions, Automation Studio, will save all this data to our central database. And then we use another program called PolyView, which we'll do is pull out all the different data in a very systematic manner, so you can compare, you can load the areas, you can compare the peak between two different plus 2, minus 2 peaks, and you can calculate the E out of it. So in a very systematic manner, you have all the data in the database to do the analysis, instead of if the data is stuck in the native computer, which is much harder to do to see the whole picture.
So Pooh, is the HPLC method applicable to all conditions without interfering from counterions?
So that's actually that's a very good question. So typically, counterion in this case, especially the initial screening, even the later screening. So when you do the initial HPLC analysis, you only have plus 2, minus 2 to think about. But when you do the true analysis, there's another counterion that may have the same UV absorption, maybe have the same retention time or similar retention time, that will interfere with the 2 peaks you're trying to see. In this case, we're lucky. We didn't, because it's really hard to predict all the things you screen will have that kind of impact. So initially, we will not worry about it. We will only do the analysis as if there are only 2 peaks. There are other situations where the counter ion, one particular counter ion, will overlap with one of the peaks. In that case, if you still typically get clues about the resolution out of if that particular compound is still a good resolving Chiral reagent or not. If that become your, which did happen before, then you start modify your condition to make sure the two enantiomer peaks separate from your counter ion peak, so you actually have a 3 peak to contend with. It's only at that time you start worrying about the counter ion peak to be interfering or not. But initially, because of the high throughput fashion, you don't really need to worry about it until that presents itself as a problem.
The next question is, Pooh, how did you know 2 equivalents of counter ions was needed?
So initially, this is something interesting because typically when you receive this happens all the time, right? When a project is sent to us, we really have 0 ideas about what's happening, right? We try to read through. What typically we'll advertise, we try to encourage our collaborators to do is to give us as much information as possible. But typically the information we get is, they try their best to say, we'll try this, it kind of worked, we'll try, the information is kind of scattered, but because that's what they tried, and then they might give up, they move on to the next, because in this case, the 2 synthetic step plus the SFC, it was the working one. So they actually kind of zeroed into that quickly. But there's other things they kind of tried, but didn't really go into too much because this SFC gave them really good results. So it kind of fixated on that. But one of the write-out, so we are trying to learn. So one of the write-out is one of the experiments they did, actually they used 2 equivalents of amino alcohol. This 2 amino indinol. But for that condition, whatever, I forgot what they tried, but it wasn't really that promising. So they got an inkling the two equivalent might be totally necessary, but it was not really explored further. So when we actually get this package of all the information they gained from all the experiments they have done, we just say, okay, the initial screen we'll just use 1-to-1 because we're trying to learn as much as we can. But after the first screening is done, we realize maybe the equivalence is actually does matter, and 2 equivalents is necessary. So that's with that hint and the more understanding from the first screen, we put 2 equivalents as one of our variables as well.
So, Pooh, do you think it's possible to optimize the conditions even further?
Initially, we did suggest to the Rutgers team to say, we can definitely modify this a little bit further because there's other, in terms of ratio, we just pick 1-to-1 propionitrile heptane. But there's, typically, that's only our starting point. There's a lot of, like what I said, there's continuous variables, right? 50-50 is 1 ratio. You can increase the heptane amount or decrease the heptane amount a little bit, make sure they're miscible, but there's still fine-tuning that can be done. There's different nitrile you can try. There's maybe even different non-polar solvent we can try to fine-tune it, like methylcyclohexane, different kind of things we can try. But because the case was so dramatic, the solubility difference was so dramatic, the team, Rutgers team pretty much just made the call, said, this condition is perfect already. We just need to, if we can replicate it at the bigger scale, no need to optimize it even further. But if in a typical setting, if you don't get this lucky, if the resolution is still, EE is still give you only 90% or 85%, whatever, there's definitely a lot of room in terms of solvent ratios, different solvent identities that within the same category that can still be explored to further optimize this condition. But in this particular case, because the result was really good, we did not go further.
Thanks, Pooh. Well, that's all the questions we had for today. If you're still submitting questions, we will keep the webinar website open for 5 more minutes to allow you time to send it. Unanswered questions will be answered privately in a follow-up email message by Pooh. I'd like to invite you to visit www.freeslate.com to see our previously recorded webinars on the application of Freeslate high-throughput research solutions. To see our previously recorded webinars, select Technical Resources from the upper navigation menu, then select Learning Center from the drop-down menu. This concludes today's webinar. On behalf of Pooh and myself, I thank you for attending, and we look forward to seeing you at future events. Have a pleasant day.